Hello everyone! Starting from this video, we're going to dive into electronics, and we will begin with the diode. Now, I want to keep this practical. We will not get lost in the internal semiconductor physics. Instead, we will learn just what you need to analyze circuits and solve problems. So, what is a diode? A diode is one of the most basic electronic components. It lets current flow in one direction and blocks it in the other. Think of it like a one-way valve for electricity. Here is the circuit symbol. The triangle side is the anode and the vertical line side is the cathode. Current flows from anode to cathode when the diode is on, plus on the anode side, minus on the cathode side. Now, in the lab, a real diode looks like a small glass or plastic cylinder with a colored band on one end. That band marks the cathode. So remember, the band is the cathode. That is all you need to know to place it correctly on a breadboard. The important thing is how the diode behaves depends on what material it is made from. The two most common types are silicon and germanium. Let us look at each one. Let us start with the silicon diode, which is by far the most common. A silicon diode has a forward voltage of 0.7 volts. This is the toll it demands before it lets any current through. Imagine a simple source, a voltage source E, a silicon diode, and a resistor R. Now, there are exactly two scenarios. Scenario 1. E is greater than 0.7 volts. The diode says, okay, you have paid the toll. I will let you pass. In this case, the diode turns on and acts like a short circuit with a 0.7 volt drop across it. So in the equivalent circuit, you simply replace the diode with a tiny 0.7 volt battery. The rest of the voltage, E minus 0.7, drops across the resistor. Scenario 2. E is less than 0.7 volts. The diode says, sorry, you have not reached my threshold, no entry. The diode stays off and it acts like an open circuit. No current flows at all, 0 amps. The entire voltage E appears across the diode and the resistor gets nothing. Germanium diodes work on the exact same principle, but with a lower threshold. Instead of 0.7 volts, the germanium diode needs only 0.3 volts to turn on. So if E is greater than 0.3 volts, the germanium diode conducts. You replace it with a 0.3 volt drop and the remaining voltage goes to the resistor. If E is less than 0.3 volts, the diode stays off. Open circuit, no current. Compared to silicon, germanium turns on sooner because the barrier is lower. However, in modern electronics, silicon diodes are far more common. They have better thermal stability and are cheaper to manufacture. You will mostly see germanium diodes in older circuits or special applications like guitar pedals. Now, there is a third model, the ideal diode. This is the theoretical model used to simplify analysis. In the ideal model, there is no forward voltage drop at all. The threshold is 0 volts. If any positive voltage is applied, even the smallest amount, the ideal diode conducts perfectly. 0 resistance, 0 voltage drop. It behaves exactly like a closed switch. If the voltage is 0 or negative, it behaves like an open switch. No current can pass. I like to think of it as a funnel. Current can enter from the wide end and come out the narrow end, no problem. But try to push it in from the narrow end. It does not fit. Now, why would we use such a simplified model? Because when you are first analyzing a circuit, you want to understand the overall behavior without getting distracted by small voltage drops. Start with the ideal model. Build your intuition, and then add the 0.7 or 0.3 later for accuracy. Now let us bring all three models together on a single graph. This is the IV characteristic curve. The horizontal axis shows the voltage across the diode, VD. The vertical axis shows the current through it, ID. Let us start with the ideal diode, shown in purple. For any negative voltage, the current is zero, flat line along the axis. The moment the voltage crosses zero, boom, the current shoots straight up. Any positive voltage means unlimited current. It is like a wall at 0 volts. Next, the germanium diode in green. Again, for negative voltages, nothing, zero current. As we increase the voltage past zero, still nothing happens. 0.1 volts? No. 0.2? Still no. But once we reach 0.3 volts, the current suddenly takes off. The diode wakes up and starts conducting. Finally, the silicon diode in blue. Same story, but it holds out even longer. 0.3? No. 0.5? Still no. It waits until 0.7 volts, and then it lets everything through. Notice the pattern. All three curves have the same shape. Flat in the off region, steep in the on region. The only difference is where the turn-on point sits on the voltage axis. Let us recap what we covered. A diode is a one-directional current device. Current flows from anode to cathode. The silicon diode model has a 0.7 volt forward threshold. Below that, it is off. Above that, it conducts with a 0.7 volt drop. The germanium diode model has a 0.3 volt threshold. Same logic, lower barrier. The ideal diode model has zero forward voltage. It is a perfect switch, on when forward biased, off when reverse biased. The IV characteristic curve shows all of this visually. In the next lesson, we will put these models to work by solving actual diode circuit problems step by step. See you there!